So did you, how's the homework doing? Oh, yeah, I started. Yeah, it's good. Yeah, I was trying to do it before, because the next one will be due tomorrow. Yeah. So. I guess let's start. It seems thinner than usual. I don't know what's happening. Was there any homework due today for some other class? Yeah, maybe let's see. All right.
Maybe this one.
Yeah. So on that note, so apparently Michael is away today, so he had like an unplanned travel, so he can't make it today. His office hours are moved to tomorrow 9 to 11 a.m. Okay, so tomorrow there are 2 office hours, both Wyming's and Michael's. So I guess that's less load on you, so it should be better. So I have this as an announcement, but on the discussion board, but just in case. Alright, so today I want to start a new thing, which is optimization, and it's this really powerful concept. So we'll do that. That'll be a topic for the next week or so, maybe 2 weeks. So just a quick recap. So last couple of weeks, what we've been seeing is randomization, right? So we've been looking at so in some sense, this is a summary of what we did. Okay, so first, we started talking about how randomization could possibly lead to efficient algorithms. Okay, and main thing here was, very often, randomized algorithms are simpler than coming up with algorithms. Like quicksort is something that you would naturally come up with, but it has a good expected running time. I also briefly mentioned this randomized min-cut algorithm, which is significantly simpler. At least the algorithm itself is much simpler than doing the classical min-cut algorithm. And we also saw examples where randomized algorithms are faster in expectation than worst case things. And we saw some unexpected examples where using randomization gives you some power that you wouldn't ordinarily have. Okay, so the example there was finding the number of distinct elements in a string. Okay, so there, if you do not use randomization, you have to use a lot of memory. And there was also this example of primality testing, where basically, you can test whether a number is prime or not very efficiently if you allow randomization. So I was surprised with the number of people who are doing this for your projects, by the way, the deterministic primality testing. So it's very good, but it's a powerful, it's a pretty difficult paper. So yeah, hopefully you won't have too much difficulty. Alright, and the main things we saw in the analysis of these things are, we saw how to analyze the expected running times, okay, and we encountered basic probability in the process. Okay, so we encountered this notion of linearity of expectation, which I said is very powerful, and it's a notion that's used all over the place. And we also saw a little bit about concentration bounds.
And these are basically bounds that say what's the likelihood that a random variable is far from its expectation. And we had multiple inequalities of that kind. So this is a quick recap. So this time we're going to shift gears, as I said, and we're going to talk about optimization. Okay, and before that, I just want you to quickly recap about. So the main aim of this course is basically to tell you guys how to approach a new problem, right? So if you see a new algorithmic problem, the question is how do you go about designing algorithms? Okay. And so far the kind of examples we've seen are, okay, so you try to see if you can formulate the objective in a recursive way. Okay, so you try to say, try to find a sub-problem or something like this and solve that and then combine the sub-problems. That was divide and conquer. In some problems we said you can cast them as flow problems, and in the homeworks you've seen some examples of what could be captured using flows. And we've also seen, okay, so if you see a new problem, one thing to keep in mind is maybe it's very difficult. So before you go about trying to find algorithms for it, you should think about whether maybe the problem is NP hard. Okay. So these are the things you would do. Okay. So today we'll see a very general technique, which is a new one, which is try to cast this problem as an optimization problem. Okay, and we'll see multiple examples of this. And this is the kind of thinking that you should get used to because it's useful for a lot of problems. Okay. So we'll see examples of this today. So what is an optimization problem to start with? So all of you probably have seen optimization in some form, right? So anyone who hasn't seen optimization in a calculus class? Okay, so hopefully all of you have seen in some form. Okay, so basically, in an abstract sense, it's very simple. Okay, so you have a bunch of variables, okay, and let's call them x1, x2 up to xn. Okay. Often I'll just compactly write them as x, which is a vector. Okay, so this is usually in Rn. Sometimes it could be in a smaller domain and so forth. And you have, and these are just variables, right? So these are allowed to take any values in Rn. And usually you have some constraints. Okay, so you have some g1 of x1, x2 up to xn less than or equal to some b1 and so on. And think of this as, if you have, let's say, linear constraints, this is just something like x1 plus 2x2 is smaller than or equal to 1 or something like this. Okay? So these are what are called constrained optimization problems. Okay? So you have variables and you have some constraints on them. Subject to these constraints, you want to optimize an objective function. Okay? So you want to maximize some function f of x, x1, x2 up to xn, subject to these constraints. So this is abstractly an optimization problem, and f and g can be of various sorts. Okay, so they could be, for now they're arbitrary functions. Okay, so they just constrain the solution set in some way. Okay, so as stated, this is a very powerful thing, right? So this can capture lots of problems. So let's see how you would cast some of the problems we've seen in terms of optimization. Okay, so I'll go over a few examples. So maybe you guys can try to come up with this. So let's look at maximum independent set. Right? So here the problem itself looks like an optimization problem. Okay, so here what is the problem? You have a graph G, and the aim is pick a set of vertices such that first you want
no two vertices in S have an edge between them. Okay. So if you take any ij in S, then there's no edge between I and j. And the second thing is you want to maximize the size of S. Okay. So this is the maximum independent set problem. We've seen this in the context of NP hardness. This is a classical NP complete problem. Okay. So, right. So how would we phrase this as an optimization problem? So what would be the variables and what would be the constraints and what's the objective function? Right, so if you want to phrase something as an optimization problem, this is what you should think of. Okay, so what should the variables be? What is the constraints and what's the objective function? So the statement itself, right? So the statement of the problem naturally has an objective. So what is that?
Maximize the number of vertices.
Yeah, so it's a natural maximization problem, right? So it is, you want to maximize the size of the set you select. Okay, so the objective function is somewhat clear intuitively. Okay, now what should be the variables? Sorry?
Vertices themselves.
That's yeah. So you could say I have one variable xi for every vertex, and it's supposed to be 0, 1. It's supposed to indicate if I pick that vertex or not. Okay, so that's a natural choice of variables, right? So most variables choices will be of this kind. Okay, so you can. So here you can have a variable, one variable per vertex, which says is the vertex pick. Okay, so this is a Boolean 0, 1 variable. Okay. So if the vertices are some 1 through n, then you have variables x1 through xn, and you also have this constraint that each xi is either 0 or 1. Okay. So for now I am allowing constraints of this kind, okay, where I say that xi is supposed to be in 0 or 1. Okay. And of course, so now how do you, so if you just have these, then any subset is feasible. Right, so how do you enforce the constraints that no two vertices in S have an edge? So you want something just in terms of the x's, right? So xi's are your variables, and you want to enforce the constraint that basically what you're saying is if you take any two vertices with xi and xj being 1, okay, if xi and xj are both 1, then ij is not an edge, right? So that's the constraint you want to, I mean, that's what this says. So how do you enforce that constraint?
Maybe give them different signs.
Sorry?
Maybe give them different signs or something like that.
That's right, but suppose I had to tell you, suppose you had to give me a set of constraints that these variables have to satisfy, right? And any x's that satisfy those constraints must actually yield a solution to this problem, right? So this is, think about doing some kind of a reduction, right? So that's essentially what's going on here. So this is some kind of a reduction from your problem to an optimization problem, right? So that's, yeah.
If you sum both variables on the sides of a vertex, that's got to equal less than 2. Or got to be less than 2.
Yeah, so this is the right idea. So what he's saying is, so suppose I take any edge, Okay, so ij is an edge. Now, could it be that both xi and xj are both 1? No, right? Because then you vertices in S that have an edge. Okay? So what you can say is that ij. Okay? So you have xi plus xj is strictly smaller than 2, or since they are integers, you can say it's less than or equal to 1. Okay? So at most one of them is 1. Now, is this good enough? I mean, are these all the constraints? So suppose you have this constraint for all ij, and suppose xi is in 0, 1, then are we okay? Do you need any more constraints? Okay, sir.
One should be greater than 0. At least one should be 1.
You don't need to have, right? In an optimal solution, if you try to maximize sum over ixi, then it's fine. I mean, it will automatically put some of them to be 1, or how many ever it can to be equal to 1. Right? So I haven't written the objective yet. Okay. So the objective is you want to maximize sum over ixi. And subject to these constraints, okay, to xi belonging to 0, 1, and for all edges ij, xi plus xj less than. So it turns out in this case these are enough. Okay? So you don't need any more constraints. And the way you should verify this is by saying, look at any feasible solution to this. Okay? So take any feasible solution to these two sets of constraints. Okay? So you get some 0, 1 solution, right? And the claim is that the set of all, okay, let me write down what I'm saying. So take any xi, and that satisfies the constraint. And now you look at S being equal to set of all I such that xi equals 1. Okay. The claim is that this is an independent set. Okay. And this you can easily verify, right? So this is easy to verify. This is an independent set. And the reason is, if it were not an independent set, then there has to be some edge. Okay, and for that edge, this constraint is violated. Okay, so that's why it's easy to verify. So since this is the easiest example, I'm going through it in like full detail. Okay, so but in general, it's easy to see these things. Alright, so it's easy to phrase maximum independent set as an optimization problem, and this is the optimization problem. Okay, so any questions about this? We'll see some more examples, so if it's not very clear, this will become clear. But this is very simple, so it should be clear. Okay, so now let's see max 3 sat. Okay, so this is something I guess many of you did in the homework. So there was this reduction from 3 sat to integer linear programming. Okay. So it's the same thing. So let's try to formulate max 3 sat as an optimization problem. Okay. So what's the problem here? You have clauses, or you have variables x1 through xn, these are Boolean variables, and you have clauses which are like xi or
something like this, and you have a phi which is the AND of these clauses. Actually, since it's max 3 sat, you can, you don't have to satisfy all of them, you just have to satisfy as many as possible. Okay. So you have phi 1 equals this, phi 2 equals some other clause and so on. You want to find an assignment. Okay. So here it's a little bit more tricky how you would write this as a optimization problem, right? So how would you write this as an optimization problem? So what would be the variables?
Variables are x1 to xn, then constraints are like they can just take value 0 or 1 because they're boolean.
Okay, so you can have, so this is the obvious thing you would start with, right? So you would say, we have variables, they are supposed to be true or false. So have them as the variables in your linear program also, right? Or in this optimization problem also. So you could have some variables xi's. Okay, so let me actually, I will need 2 slides for this. Let me create a. Okay, so you have variables. So xn, each supposed to be 0, 1. Okay, each xi is in 0, 1. So this is very similar to before, right? So if it's true, you want to set it to 1, otherwise 0, right? So if it were just a satisfiability question, then what can you say about a clause if it is satisfiable? Can you write a linear constraint that captures if it's satisfiable or not? So this is what you've seen in the homework, right? So basically, if a clause is satisfiable, then you will have x1 plus x2, or rather, let's look at this clause. So then you'll have xi plus xj plus 1 minus xk. You will have this to be bigger than or equal to 1. Okay. If it's bigger than or equal to 1, then it means that, so
that clause is satisfied.
yeah, so inequality satisfied if and only if clause is satisfied. Okay, so this is clear for everyone. Okay, so this is fine. Okay. So this is one thing you can write. But now the problem is to maximize 3SAT, right? So is to find an assignment that maximizes the number of clauses that are satisfied. Yeah.
You're saying 1 minus xk, so what if xi is 1 and xk is 1? That's going to equal 0.
Sorry? No, it will be 1, right?
So if xi is 1, that's 1, but
Yeah.
1 minus 1 on the other side. Oh, okay, so that is 1 here. That's
Yeah.
Gotcha. Okay.
So each, the way to think about this is both xi and 1 minus xi are either 0 or 1. Right, so if one of them is 1, then you're closed.
Gotcha.
Yeah, so
But in 3SAT, you're saying that every clause has to be satisfied.
yes.
So then what do you mean by max 3SAT? If you say the maximum
No. So max 3SAT is a slightly different problem.
So your
So-
entire thing need not be satisfied.
Yes. So the problem here, so this is a good point. Just to clarify what the problem is. So the problem is just you have a bunch of clauses. Each clause has 3 literals, and you want to find an assignment that satisfies the most number of clauses. Okay.
So that is the problem. You don't have to satisfy everybody. Okay? So if you had to satisfy everyone, then this is what you would write, right? So you would just say, find me some x's such that each xi is in 0, 1, and for every clause you have this constraint. Okay? Now suppose I don't need every clause to be satisfied, I just need the maximum number of clauses to be satisfied. Now this is an optimization problem. Okay? So how would you try to cast this as an optimization problem? Yeah.
Just maximize the sum of each.
Yeah, it's a great guess. Okay, so you might say, okay, so if it is satisfied, this has to be 1. Then you can say, okay, so now I'll have the sum of these things as the objective, right? So the question is, what should the objective be, right? So the objective, guess for the objective is the sum of these things, right? So sum over clauses phi of the literals in that clause, right? So you can say xi plus xj plus 1 minus xk kind of thing. This is bad notation, but you know what I mean, right? So it's if it's sum over clauses, whatever was there in that clause. So, right. So this is natural, but I claim this doesn't quite capture what's going on here. Why? Anybody see why this doesn't? Yeah.
You have like 3 literals that are all true in one clause, and
Yeah.
you satisfy that one clause, but you could have satisfied multiple if you.
Exactly. So is that point clear? So basically, this is not. This doesn't quite capture this fact, because if you have one clause being satisfied by 3 literals, as you put it, then this will contribute 3 to the objective, while it should only be contributing 1. Okay. So one way to write this is to say, okay, so I will do min of. You could do this. So since we are allowing arbitrary objectives, you could just say, try to maximize sum over all clauses of min of 1 and whatever that number was, right? So it was like xi plus xj plus 1 minus xk. Okay. So this is something you could do. And if you want to be really formal about this, you could introduce a new variable for each clause. Okay, so you could introduce some y phi, which is a new variable for each clause, and you can say y phi is also either 0 or 1, and then you can say that xi plus xj plus 1 minus xk is bigger than or equal to y phi, and then you maximize just sum over the clauses phi of y phi. So firstly, all of you see this, that maximizing the sum over clause of min of 1 and that, so that takes care of the problem that you mentioned, because if this quantity is 0, it will contribute 0. If it's anything more than 1, it will contribute 1. And you can also make that more formal by saying, you can have a new variable that captures the minimum. Okay, and that's what I'm calling y sub phi, and that's supposed to be 0 or 1. Okay, and and then you must have these things adding up to at least y sub phi, because and your goal is to maximize this. Okay, so if they happen to add up to at least 1, then you will set y sub phi to be equal to 1. Okay, so you can verify that these two are equivalent. So easy exercise. Verify that the two are equivalent. So, any questions about this? Okay, so if you don't see it immediately, it's actually very easy if you try to work it out.
Okay, so now let's look at another example of something we've seen. Okay, so max flow, right? So here you have directed graph with capacities. And you have a source and sink. Okay, minus S minus T. And your goal is to send as much flow as possible from S to T. The issue? Alright, so the goal is send as much flow as possible from S to T. Okay, while respecting all the constraints and these flow conservations, right? So how would you cast this as an optimization problem?
If you were to have all the paths to S to T, you can
Okay.
maximize the minimum weight across the edge with the minimum.
The edge with the minimum. Oh, for every
You
path?
have an edge with the minimum weight which will sort of be
Okay.
your flow.
And then you've got to have edge disjoint paths.
Yeah.
So you could write it, but the number of paths is exponential. Okay, so it would be an exponential sized program. So that is actually a useful formulation, but we'll come to that later, because right now we want formulations that are small, okay, that are polynomial sized, let's say. Because if you are casting it as an optimization problem and you hope to just solve that optimization problem, that had better be compact, right? So in fact, I'll show one example where there is no easy way to write it in a compact way, but for flows you can. Okay, so any other variable, choice of variables?
So the flow on each edge could be a variable.
Yeah, so this is how we define flow, right? So we define flow as just mapping from edges to real numbers, right? So you could just have that. Okay, so Fe, the variables, Fe, which is the flow on every edge, on edge E. We used to have a professor who used to ask, is that for me? I don't want to do it. Yeah. So anyway, right, so we have flow on every edge, and now this time we don't have any integrality constraints, right? So these are allowed to be arbitrary real numbers, and that's fine. Okay, so our phrasing of optimization problems allows arbitrary numbers. Okay, so Fe, maybe it always has to be bigger than or equal to 0. Okay, so there are real numbers that are bigger than. And so now what are the constraints?
Capacity.
Okay, great, yeah. So capacity, Fe on every edge is smaller than or equal to capacity of E. Any other constraints?
Flow coming in is equal to flow going out.
Yeah, so flow conservation for every vertex apart from the source of the sink, right? So for all U which is not equal to S comma T, not in this set S comma T, we have, yeah, so let me just write it as sum over so I don't know if I should introduce notation or not, but let me introduce it. Okay, so E plus of U is the edges that come into the vertex U, let's say. Okay, so this is what I'll call E plus of U, Fe minus sum over E belonging to E minus of U, Fe equals 8. So E plus is a set of edges that come into U, okay, E plus of U. and E minus is a set of edges that leave U. And this is exactly what flow conservation amounts to. Right? And this is true for every U that's not one of S and T. Okay. So great. So these are the constraints. And what's the objective?
Maximize the sum of that over every edge.
Some of those.
That's the total value of the flows, right? But what's the actual flow going from S to T?
So you want to maximize the sum of the edges coming into T.
Yeah, so coming into T or going out of S. That captures the actual amount of flow that's going in. Right? Is that clear? Yeah. So we want to maximize sum over E in E minus of S of F. Okay. So you want to maximize the amount of flow starting at S. And this is it. Okay, so in this case, one thing to note is that all constraints are nice and linear, and the objective is also linear. Okay. So we'll come back to why that's important in a bit, but this is one thing to note. Alright, so this is one formulation for max flow. Now, having just told him that you always want to come up with compact linear formulations, let me give an example where it's very difficult to come up with a compact linear formulation, okay, compact formulation. So this is the minimum spanning tree. Okay, so what's the goal here? So there are some problems in which I want to illustrate the constraints are pretty complicated. Okay, so this is one such example. And maybe in the homeworks you'll see an example of scheduling where also it's tricky to figure out what the constraint should be and what the variable should be. Okay. So here, so what's the problem? The problem is you're given, let's say, a weighted undirected graph. And the goal is to choose a subset of edges, okay, such that first you want all the vertices are connected. So that's what we mean by a spanning tree. Okay, so there should be a path from every vertex to every other vertex. And you must have, there exists path from U to V for all UV. And of course you want sum of weights to be minimized. So what would be the formulation for this kind of thing? So the variables and the objective are clear, right? So what should the variables be? Guess on variables.
Edges.
Yeah, you want to pick a subset of edges. Okay, so it's just natural to say I'll have one variable for every edge, and you either pick it or you don't, right? One for each edge. Right, and it's supposed to belong to 0, 1. And yeah, so and the objective is now clear, right? Objective is just minimize sum over E, the weight of the edge times whether the edge was picked or not. So this is again clear. So what are the constraints now? You want to pick a collection of edges so that for every pair there is a path, or so that what you get is a connected subgraph. So any guesses? How would you write the constraints?
There exists a path between any vertex.
Yes, but how would you force that?
You could choose one arbitrary vertex and take the distance from that. Must be finite.
Oh, but how would you measure that as just a function of these x's?
The sum of all the edges between two vertices.
I agree. But how would you, what do you mean by edges between two vertices? Right, I mean, every edge is kind of between vertices. Yeah. So this path idea can be made to work if you really want. Okay, so you can say that you look at all paths and say that in some sense you've got to pick one edge, one path fully or something like this. Okay, but it's tricky to write it. So there's a somewhat tricky, easier formulation, but it turns out in this case most natural formulations you come up with will have exponential size. Okay, so let me write an exponential size one, and I'll tell you how to write a poly size one. I won't actually write it. So the exponential size linear program it basically says you look at any subset of the vertices. Okay, so this is all of V, and you look at any subset S of V. Okay. This is a subset of the vertices. Okay. Now, could it be that there is no edge that goes across that is picked? No, right? Because basically if none of the edges in this cut of SS bar is picked, then it means that there is no way of going from a vertex on this side to some vertex on this side. Okay? So this is what it says. So you can say that for all S, you can say that sum over E belonging to cut of SS bar XE must be bigger than or equal to 1. Okay. And of course XE has to be in 0, 1. Now, is this enough? So suppose you have some x's that satisfy this constraint for all S, okay, for all subsets.
So are all vertices inside a subset connected? Are we assuming that, or within a
Yes, so you are assuming that the problem is feasible. So otherwise this will be infeasible. This will be infeasible also. Okay, so if all the vertices are not in any, are not connected, then this is infeasible also.
within S? So within that subset S?
No, we are not assuming that. So what we are saying is for every set, it must be that there is at least one edge which goes across. And the reason is otherwise it doesn't matter if S was connected or not. You can't get from a vertex on one side of S to a vertex on the other side of S. Right, so now let's say you have some x's that satisfy these constraints for all S. Then I want to say that what you get is a connected graph. So why is that? again you can argue by contradiction, right? So you can say, suppose the graph you get is not connected, and now you could say, okay, I have a 0-1 solution, okay, where suppose it's not connected, that means that there are no edges going across. That's by definition, and that constraint will be violated. So maybe you should think about this for a bit and ask me a question if you. So what I'm implicitly doing for each example, if you guys haven't noticed, is I'm writing down a set of constraints, and then I'm arguing that this set of constraints is enough. Okay? So I'm trying to show that any solution that satisfies this set of constraints actually translates to an actual solution for the problem. Okay? And this is something that you need to do. So in that sense, it's exactly like a reduction. Okay? So you prove that these constraints capture the problem you want. Yeah.
Do we need to make sure there's no cycles to create a spanning tree?
That will be captured by this minimization. So that's the nice thing. You don't have to, you could write a constraint. You could say that, you could say for every cycle, the sum of the edges is strictly less than the length of the cycle. Okay, but you don't need that, because any solution that minimizes this is just, yeah. So this is like saying, find a minimal connected graph, okay? A minimum weight connected graph, subgraph, and that will have to be a tree. Okay? So you don't have to force that it's a tree. Yeah, so that's a good point. So, right, so now suppose I had to write a polynomial sized constraints, okay, constraint set. Then what would I do? I mean, you can now, the hint is, you are writing something about cuts, right? So could you use max flow min cut theorem to say something? So I'm saying the value of every cut in the graph is at least 1. Yeah.
The minimum cut then must be at least 1.
Yeah, exactly. So in some sense, this captures this intuitive notion we had before, that between every pair of vertices there must be a flow of at least 1. Okay, because there's a path of there's at least one path, right? And that you can write, and then you can have for every pair of vertices I and j, you can now write a flow linear program, just like we did before, where you say that, and now the flow edges are these same x's, fe's are like the x's, and you can say that it must satisfy whatever inflow equals outflow and so on. Okay, so I won't get into that. Okay, so you can figure out how to write this. So it turns out for spanning tree, just directly coming up with a poly-sized thing is very artificial, but going via this cut actually helps. Okay. So this optimization formulation is natural, right? Because you say that I want it to be connected, so I don't want disconnected pieces, which means that for every s there has to be one edge going out. This is for all s that's not the empty set or V. Okay, so you don't want the trivial. Okay. All right. So this is how you can write spanning trees. Okay. So it turns out for most problems you can come up with this kind of optimization framework, optimization formulations. Okay, by picking and the thing you have to worry about all the time is you have to think about what the variables are, what the constraint set is, and what the objective function. Okay, so these are like the three main things.
and this is what defines an optimization problem. Okay. And abstractly, optimization problems look like this. So you have variables x1 through xn, and which I just write as the vector x. And you want to minimize or maximize some f of x, and you have a bunch of constraints. G of xi is bigger than or equal to 0, or something like this. And many times, if you have constraints like xi is in 0 or 1, you can write it as just xi squared equals xi, for example, and this would capture 0, 1. So, or alternatively, you could have like a domain for x. So this is typically what we mean by an optimization problem. And one viewpoint that often helps is what I refer to as the geometric viewpoint. Okay, so if you think of these, if you think of all the feasible points, okay, which is all the x in Rn such that x satisfies all these constraints. Okay, so you have a bunch of constraints, and I'm looking at set of all x's in the n-dimensional real space that satisfy this, such that x satisfies all constraints. Okay. And this will typically be some subset of Rn, right? So it is if n is 3, let's say, then you have 3-dimensional space, and you have, let's say, x1, x2, x3, and there is probably some region that satisfies all these constraints. It doesn't always have to be a region, it could just be a subset of points. Okay, so if, for instance, you had every xi has to be 0 or 1, right? Xi is in 0 or 1, then there are only 8 points total that are satisfied, that are in this feasible space. Of those, maybe a few will be satisfied. Okay. Is the geometric notion clear? It's actually very simple. It's just so this is what I'm calling the feasible set. Okay, so this is a set of all x's that satisfy all the constraints. Okay, it is some subset of Rn. All right, and now what we are asking is, you want x to belong to this feasible set, and you want to maximize some function g of x on it. So you want to maximize some function f of x on it, minimize or maximize. Subject to x in this feasible set. So if these feasible sets are simple, then it's actually this kind of geometric viewpoint is easier. Okay, so as we will see next time. So before we go there, what I want to start off with is this general thing that you should know. So you can phrase a lot of problems as optimization. Okay? As we saw, you can phrase even NP-hard problems like max 3-sat and so on as optimization problems. So the question which is natural is, what kind of optimization problems can you solve efficiently? Right? I mean, clearly we don't expect to solve the optimization that we got from independent set, right? Because independent set is NP-hard. So we don't expect to be able to solve this efficiently. Okay? So the question you want to ask is, what kind of optimizations can we solve well? And it turns out one very important convex optimization problems. So define these things in a bit, but basically this is a set of problems, this is the class of problems where the objective function, which is this f of x, okay, so remember you have this minimize f of x, right? So the f of x is convex. And you have a minimization problem. The goal is to minimize f of x. And the feasible set,
okay, which is the set of all x that satisfy all the constraints. It is what is called convex. Okay, so how many of you have not seen the notion of a convex set? Okay, there's at least some. So we will define that, but I just wanted to get a sense. And how many have seen it multiple times? Okay, only a few. Okay, so yeah, so then it's good to see it again, because this is one notion that's very fundamental in computer science. All right. So first, the notion of a convex set. Okay. So convex set is basically it's a set of points in Rn. Okay. So it's let's call S is the set. Okay. It's a subset of Rn. Okay. And which has this property that if you take any 2 points x and y in S, the entire line segment joining x and y is in S. Okay. So that's when you call a set convex. Okay. So if you have a set that looks like this, then it's not convex. Why? Yeah, so if you take 2 points like one here and one here, then yeah, so you have points on this segment that are not in S. Okay, so this S is not convex. Okay. And if you have any discrete set, it's not convex. Okay, so if I have something like just 0, 0, 1, 1, something like this, if I just have 4 points, okay, then this is not convex. Again, just because if you take any point on this line segment, it's not there in the set, right? So no discrete set is convex. Okay, so that's just a trivial fact, but it's just good to remember because convex, unless it's a singleton or something. And this is why if you have a feasible set which let's say is a subset of 0, 1 to the n, like we saw a lot of problems where like independent set, right? So we wrote xi belong to 0, 1. Okay, so this is a discrete set, right? So these kind of things are not convex by definition. Okay, so that's why you could capture NP-hard problems using these kind of things. Okay, so this is what a convex set is. It's a relatively simple notion. Now what's a convex? Right, okay, so I wanted to have more examples. So these are examples of some things that are not convex sets, but what are examples of things that are? Okay. So the canonical example is the ball. Okay, so it's a set of all points that are at a distance less than or equal to 1 from the origin. Okay. And this, as you would imagine, picture is obvious, but you can also prove that this set of points is convex. Okay, so if you take any 2 points in this set, then the entire line segment will lie on this. Okay. So sometimes these kind of things take a little bit of work to prove. Okay, but it's in this case you can prove it. So actually, how would you go around proving that a set is convex? So suppose I wanted you to prove this fact formally. So what would you have to do?
Basically, you would have to, for any 2 points, you take the line joining there. Any point on that line you'll have to show
Also satisfies.
the.
Okay. And that could be non-trivial. Okay, so like in this case, what you have to do is take any point A and any 2 points A and B, and what is an arbitrary point on this line segment? Actually, what is its midpoint? Yeah, the midpoint is A by 2 plus B by 2, right? So it's A plus B divided by 2. Okay. And what's an arbitrary point? If I want, I mean, how would you parameterize an arbitrary point? So if I wanted to get a point that's close to A, let's say, how what would it be, right? So let's say I wanted a point that is 1/3 of the distance from A and 2/3 of the distance from B. Okay, so what would that point be? So this is somewhat easy coordinate geometry. Okay, so this turns out to be like if you want a point like that, it would be 2/3 A plus 1/3 B.
Basically AM plus BN.
Yeah, so in general, any point on this line segment joining A and B will be something like lambda times A plus 1 minus lambda times B. Okay, where lambda belongs to 0, 1. So if lambda is 0, you get B. If lambda is 1, you get A. And as you go from 0 through 1, you get all the points between A and B. Okay, so these are just these are what are called convex combinations of A and B. Okay, so yeah. So hopefully all of you have seen this in some form or the other, right? In old calculus / geometry classes. So I just want to recap because this will come up. So this is how you define. So you write this out and try to show that if A satisfies this inequality and B satisfies this inequality, then this point, which is called C, also satisfies this inequality. So in this case, it's not that easy. Okay, so you'll have to do some algebra to show this. Okay, but let's not get into that. Okay. But is this notion clear? Like any point in the middle, you can write it as lambda times A plus 1 minus lambda times. Okay, any point on the segment. Okay, so this is one example of a convex set. The other more easy example is, easy in the sense of proving that it's easy, is our linear constraints. Okay, so these are constraints of the kind some linear combination of the xi's is less than or equal to b. Okay, so an example could be 2x1 plus 3x2 is less than or equal to 2. Okay. And if you just have two variables, and how do these things look like? So what is so if I just say I have two variables x1 and x2, so their feasible region is subset of the two-dimensional plane. Okay, two-dimensional real plane. Okay, so this is x1, this is x2, and everything is feasible, and you need this additional constraint. So what would be the feasible set for this constraint? Yeah, so this again is is basic coordinate geometry. So you will have a line. I don't know if it should be this or this, but it should probably be like this. But anyway, so and side of the line will satisfy. Okay, so this is what is called a half space. Okay, so a constraint like this is called a half space because if you think about it, you have the whole space, and this one constraint is cutting the space into two regions, right? One region you have less than or equal to 2, the other region you have bigger than 2. Okay. And everything on this side is what's called a half space. Okay. And this kind of a picture generalizes to higher dimensions. If you haven't seen this, you should see this. I guess everyone who's in machine learning class would have seen this, right? Because this is how the perceptron type algorithms work. They try to find the half space. And yeah, so that's basically the idea. You want to divide the whole space into two regions. This is what one linear constraint does. And this is convex because if you take any 2 points on one side of this space, I mean on one side of this plane, then the whole segment will lie on the same side. And this you can easily prove because actually this turns out to be much easier to prove than that. Okay. Alright. And the other nice thing about convex sets is that they are closed under intersection. Okay, so if you take two convex sets, take their intersection, then what you get is a convex set. And that again is true by definition, right? Because take any 2 points that are there in both of these sets, the whole line segment has to be in both of these sets. Okay, because by the convexity of the first one, the whole line segment has to be in the first, and by the convexity of the second, the whole line segment has to be in the second. Okay. So this is again easy. And this is nice because just these two together will tell you that a lot of complicated objects are all convex. Like if you take a bunch of linear constraints and you say, I take all the x's that satisfy all these linear constraints, then the intersection of these is again a convex set. Okay, so you could have several linear constraints like this. Okay, so one side is this, the other side is this. Okay, sorry, this one. So each one is, so I'm just drawing half of this, right? So this linear constraint says everything on this side, this linear constraint says everything on this side, and so on. And now the intersection region is the stuff in between, and this is convex. True from the picture, but it also follows from this. And you could have some intersection of a sphere with something else, with some convex things, and it will also be convex, and so forth. Okay. All right. So this is just an illustration of examples of what convex sets are, and I also wanted to set up some basic coordinate geometry notation. Alright, so this is a convex set. Now what's a convex function? Okay. So convex function f. So this is f, and actually can someone tell me the definition of a convex function? Because I think everyone would have seen it in one way or the other. If you have a one variable function, okay, so if I have f that just maps real numbers to real numbers. So here, all of you, how many of you have seen this notion of convex functions? At least in one dimension. All of you, I mean, you don't have to remember it, but at least seeing it. So that all of you would have, right? So anyone who's taken a calculus class would have seen this. So basically, the way you define, way most calculus books define it is by saying the second derivative has to be non-negative all the time. Okay, so it will say that d square. So this is x. This is some function of x. Let's say d square f by dx squared is bigger than 0. Bigger than 0 for all x. Okay, so and then you will draw the picture that it has to look like this. Basically, yeah. And the line is also convex, but okay. So this is one way to define it, but this is nice only for single variate functions. Okay, so for multivariate functions, where now we have f's that are actually that map Rn to R, right? So they take n parameters as input. They have n variables. So you have f of x1, x2 up to xn. And for these kind of functions, how do you define convexity?
Yeah.
Isn't it just where the derivative with respect to each function is greater than or equal to 0? Or with respect to each variable is greater than or equal to 0?
Not quite. So you could ask, so firstly, it's not the derivative, it's the second derivative. Yeah, but even that is, it does not suffice. Okay, so it turns out the right way to define this is by looking at what's called the Hessian. But I won't go into that. So what I will do is a much simpler thing, a much simpler definition. Okay, and it turns out to be exactly equivalent to the Hessian definition. Okay, so the definition basically says that if you take for any 2 points A and B, points X and Y, let's say, you have f of lambda x plus 1 minus lambda times y. So this is, as we saw before, if this is x, this is y, this is just some point in between, right? So for any and for all lambda in 0, 1. So this must be smaller than or equal to lambda times f of x plus 1 minus lambda times f of y. So this looks a bit mysterious, but you should always just think of lambda as being half. Okay? Then this is saying something very easy. Then it's saying that f of x plus y by 2 is less than or equal to f of x plus f of y divided by 2. Okay? So the average of f of x and f of y is bigger than or equal to the f at the average point. So in a two-dimensional, in just a one-dimensional function, what does this mean, right? So this means, so if you have a function that looks like, actually maybe, yeah. So if I have a function that looks like this, okay. Now this is x, let's say, and this is y. Okay. So what is f of x? This height is f of x, right? This is how you plot a function. Okay, so this height is f of x, and this height is f of y. And f of x plus f of y divided by 2 turns out to be this height. Okay, so this height is f of x plus f of y by 2. Okay, so it's this right hand side. Okay, so this is because it's the average of this height and that height. Okay. And what is f of x plus y by 2? So this point is just x plus y by 2. So this is the midpoint. And f of that is this height. Right? It's this small height. Okay. And in this case, it is true that f of x plus y by 2 is smaller than f of x plus f of y by 2. Okay. And this should happen for every x and y. Okay. So that's what convexity means. Okay. So if you have a function like this, for example, then this will not be convex, because if you take a point here and a point here, then the average of the f values is this, and f at the average is this. So basically the height at this is x, this is y. In this case, f of x plus y by 2 is bigger than f of x plus f of y by 2. So convex functions, that's why we draw them like this, and this turns out to be an equivalent definition to standard definition. So one thing which reminds me about what he said before is, what he said is that a multivariable function is convex if it's convex along each coordinate, right? So that is not quite correct, but it turns out the Hessian condition I mentioned is equivalent to saying it's convex if it's convex along every direction, okay? Not just a coordinate, but let's say you look at any direction. Okay, so direction is just given by
some a1, a2 up to an. Okay. And this is just any direction. So if you have the plane, think of it as, so this is x1 and this is x2. So now your function looks like some kind of an envelope, right? So at every point you have some value of the function that will be some three-dimensional thing. That will be the height in 3 dimension, in the third dimension. And now if you look at some direction like this, then you just get a single variable function, and that has to be convex. Okay, and in this standard derivative notion. Okay, so yeah, if you follow it, it's fine. Otherwise, just think of it as any function that satisfies this constraint. And in fact, these two constraints are also equivalent if you assume f is continuous. So it's basically the same. Okay. So this is all you usually have to remember. Alright, so any questions about convexity, convex functions? Okay, so what I said before is, so why did these come up, right? So the reason these came up is because we were asking, when can we solve optimization problems efficiently? We said that one sufficient condition when you can solve it efficiently is you have a convex objective and the feasible set is also convex. There are a little bit of caveats, but usually if your feasible set is convex and your objective is convex, you can solve this problem efficiently. So there are some numerical issues that you have to basically verify, but this is broadly true. Alright, so I wanted to go back to this example of independent set because, and in this case, I guess it's too much to do this, but basically what I wanted to say is here, the feasible set is a finite set, okay, because you have, I mean it's a discrete set because it's a subset of each xi is in 0, 1, okay, so it's a discrete set. Okay, so in this case, the feasible set is not convex. Okay. And this is one reason you can't appeal to the previous thing and say that, hey, I can solve this in polytime. Okay. And which makes sense because independent set is hard. Okay. But the objective is linear though, objective is convex. In fact, linear. And maximum flow, this is something I said before. Here it's actually very nice. So all constraints are linear. Okay. And I said that if you have a linear constraint, it's just a half space. The set of solutions is a half space. And if you have multiple such constraints, then it's just intersection of these half spaces. Okay. So the feasible set is convex. Set is an intersection of half spaces. And which implies convex. And your objective function is also linear, right? So objective function is also convex. Okay, so for this you can actually appeal to this previous theorem and say that so now you have a linear objective, linear constraints, so you can actually solve this in polynomial time. Okay, so this is another alternate way to solve max flow. Okay, so to say that this is actually, you just have linear constraints and a linear objective. So this is actually, you can solve it using what's called linear programming. Okay, so this is what we will do next time. So this is the special case that we will focus on next time. Okay, so it's and this is what is called linear programming. So it's basically optimization where you have a bunch of variables and all your constraints are linear. So they are linear equalities or inequalities, and the objective is also linear. So the objective function is also linear. And max flow is one example of a linear programming problem. And we'll see next time. I'll basically mention that linear programs can be solved efficiently. And yeah, so that's another way of doing max cut, for example, max flow, for example. All right, so let's.
Well, I would see what